So, hi everyone. My name is Gil Tene. I'm the CTO of Azul Systems, and hopefully you're in the right talk. What we're going to cover in this talk is pretty simple. It's an educational talk about garbage collection. It's not a talk about how to tune a collector. It's a talk that is intended to get you to understand how this machine that is a garbage collector in general works. And hopefully with that knowledge, you can use your own brain to figure out what to do and how to play with the various settings or configurations or issues you might run into. You'll learn a bunch of things, and I like to tell people, be careful with what you do with this, because the first thing people like to do is start experimentation, and that's fine in a lab, but don't conclude things too fast from here and taking them into production. And since at Azul we make a garbage collector that we're really, really proud of, I promise I won't be telling you about how great that collector is until the very end of this talk. Part of it is because I want you to understand all the terminology so you can really understand why our collector is as good as it is. But this is not a commercial pitch of our product, just to be clear. It's a little echoey on sound here. Is this working okay? Sorry, okay, good. Because I can hear myself from all directions here. Okay, so a little bit about me. As I said, I'm the CTO of Azul Systems, and I've really been working on garbage collection for a little over a decade now. Really looking at different approaches, or approaches that are counter-trend or counter to how the rest of the industry seem to approach garbage collection, at least in the commercial sense. Here's some evidence of me working on garbage collection. This is a real picture in my kitchen in 2004, and that is a trash compactor. Its compaction was not working the way I wanted. It was pausing. So I took over the garbage collection book, and it really did get stuck, but it was a great opportunity for a picture. But on a serious note, I had actually built collectors, both the pauseless and the C4 algorithms, which are published in peer-reviewed papers, are ones that I've created along with some other people at Azul. And I've built a lot of other things, not just garbage collectors, JVMs in general, operating systems, device drivers, firewalls and networking equipment, and big Java management systems for millions of subscribers. So I've played around with a lot of parts of the overall stack. Building JVMs came to me as a result of the others. So a little about Azul before we get into the beef of the talk. At Azul we have one mission, and that's to build scalable virtual machines. And we basically have had the approach of doing whatever it takes to make that happen for about a decade. And whatever it takes included some very interesting and sometimes seemingly crazy things, like building our own hardware, building our own instruction sets, building our own chips. This is a schematic of a 768 gigabyte machine with 864 symmetric cores in it. We actually build and ship things like this. And we delivered 3 generations of Vega, which is this architecture. But about 4 years ago, we looked at the hardware roadmap for commodity servers and concluded that we don't have to build our own hardware anymore, because the stuff we used to need custom hardware for is now available, is going to be available in commodity hardware. And as of about a year and a half ago, we are focused primarily on software. Our product is called Zing. It's a JVM that's focused on Linux, x86, and delivers a lot of what we used to need custom hardware for, 8 years ago to deliver now. We're known for garbage collection. We're known for elastic memory, some virtualization tricks, but most people associate it with the big JVMs or not pausing, and our products pretty much do that, but across a wide spectrum. Okay, so how are we going to do this talk? We're going to cover some fundamentals and key mechanisms of GC. I'm going to talk about terminology and metrics with specific terms and try to define some of them. We'll then look at using those terms to classify actual current commercial collectors you can get your hands on, so you can understand what their mechanisms actually do. I'll get into a problem I call the application memory wall problem, or simply put, why stop the world is a big problem, and then talk about our beautiful C4 collector that's actually a solution to that problem towards the end. So before I get into that, I like to ask audiences this size a question almost always, which is, how big is your heap size? And I'm not asking you what your application does, just how big is the heap size in your application. So how many of you have more than half a gigabyte of heap? Okay, a lot of you, most of you. Okay, how about more than a gigabyte? Still, more than 2. You can keep your hands up in between them and just drop them when they're done. More than 2? Okay, a little fewer, but still a lot. More than 4 gigabytes. Look around. Okay? And it's not just people getting tired. More than 10 gigabytes? Fewer and fewer courageous souls. More than 20? 1, 2, 3, 4, 5. More than 50? Ooh, we have a winner. Yeah, oh no, 2 of them, it's a tie. Oh, 3. Well, it's a demonstration, and let me show you how good this controller works. See right there? That's where you guys were. That's an educated guess. I've been doing this for more than 2 years, and the audience always falls into this bucket. You know, vast majority is there, and there are some courageous souls that have more than that. I'll get back to why this is very important about 20 minutes from now, but keep this in mind. So, why should people care about how garbage collectors work, or understanding a little about how it works, not just this invisible gift you get from a JVM? I like to use an example, a real world example, and I call this the story of the good little architect. And it's a real thing that we've run into, and it exemplifies why understanding GC is important. An architect, being a good architect, is first and foremost dependent on your ability to make other people do what you decide to do. Actually impose an architecture on a project, on a team. If all you know is how to do things right, but you don't get other people to do them, you're not an architect, you're a philosopher. And that's the key quality a good architect needs to have. And, you know, you'll see their work throughout the project, not just in their code. And early in Azul's pauseless GC world time, this is 6 or 7 years ago, we ran into an actual application that had 18-second pauses, which for us was unheard of. So we investigated to see what this application does. And we found that every time our collector ran, it dealt with tens of millions of finalizers, of objects being finalized in every GC cycle. And we were doing finalization as a stop-the-world operation at the time. So since then, we've stopped doing that, and we can handle even those concurrently. But we're trying to figure out where this comes from, because it's very rare to see that kind of volume. So we looked at the code, and we found out that every single class written in this project over a period of 2 years, somebody gets it already, had a finalizer. Now, can you guess what the finalizer did? Oh, here's what it did. It put nulls in all the fields. And it did it to help the garbage collector along, to make it not have to chase these pointers that have things in them. And this was imposed on the entire project. We saw every single class they wrote had this. It was architecture. Now, it's a little funny if you understand how garbage collectors work. It's sad, maybe. But the thing is, this is exactly the right architecture for a C++ application. When you write in C++, you need to be very, and you have a large project, you have religious destructors going around, cleaning up and making sure things are closed, and that links are broken between things. And if you have a circular linked list, something breaks it apart. And these things are really needed. So it's exactly the right thing for a C++ architect to do. But when that C++ architect moves to a Java project, they should learn a little about how the collectors work. Because this is exactly the wrong thing to do in a garbage collected environment. It's the worst thing the garbage collection can have done to it, as opposed to something that helps it along. So hopefully that example explains why this talk exists, or at least some of why you should care. So when I look at what people think garbage collectors do, or how they do them, I find that most of what people seem to know is actually wrong. And it's often wrong in a good way or in a bad way. Or Often garbage collection does better than you think, and these are examples of much better. For example, GC is extremely efficient. I'll get to exactly what that means in a few slides, but garbage collection is super efficient. It is more efficient than malloc. It's more efficient than any other form of allocating memory that is not in a stack. And you'll see the math for this in this talk, okay? In addition, dead objects cost us nothing to look at in all the fast collectors that exist in all the JVMs today. There are no cycles spent on dead matter at all. That's an important thing that most people don't get right up front. A third one is garbage collection doesn't need help to find dead objects. It will absolutely find everything that is dead and not reachable every time. No ifs or buts. There are no linked lists that can hide from it. It doesn't have to reference count anything, at least not in JVMs and precise collectors. So these are all good qualities, and most people don't necessarily think the collectors are that good, and they are all this good. This is not specific to one collector. However, the reverse is also true. There are a lot of things that collectors do that are much worse than you think. And for example, most people believe that they can tune a JVM so it won't pause a lot. And unfortunately, most JVMs, you will absolutely see a 1 second pause per live gigabyte, roughly, something on that order. And all you can do is change the when and the how often, but not the if. So that's one thing. Another one is garbage collection will find dead stuff, but it won't stop you from leaking memory. If you keep retaining things, memory will grow. So it does eliminate an entire class of memory leak bugs, but not all memory leak bugs. And then the last one, which unfortunately I see quite a bit of, is that when you do tune a collector and you've taken the bad thing and tuned it until you had a working test that passed the requirements and criteria, most likely you didn't solve the problem, you just swept it under the rug. I often see people have a criteria for a 1 hour test, ramping certain users, pausing only so much, or having a certain percentile. First time they run it, it doesn't work, so they tune it. Still doesn't work. After 3 days of tuning, they got it to work. What they really did is move the bad thing to minute 61. It's pushing it to the future. That happens a lot. And unfortunately, this is a common artifact of how garbage collectors are tuned. It does not occur in non-garbage collected environments, which is why it's a specific problem to GC. So that's some of the general things about it. I like to say that trying to solve GC problems in application architecture is something that's doable, but iffy. It's hard, it's dangerous, you need a lot of experience, and it could go badly wrong. The thing to keep in mind when you're designing your application for a garbage collected environment, thinking of how to control your allocation rate, your heap size, your morphing or lifetime of objects, remember you're not the only one writing code there. And most likely in Java, you're leveraging a lot of other people's code. Some of them work with you, some of them work for other companies. And not all of them are going to write code the way you decided to. So if you're going to leverage other people's code, you just have to live with their allocation behaviors. You don't have that much control over it. You do have certain things you can do, and these are all example techniques of ways of working around GC limitations, circumventing them, dealing with them, and none of these are wrong per se. Each one of them has a use. But almost inevitably, if you use any of these techniques, you're building a garbage collector. And unless it's a very simple problem, you probably don't have the 10 years of investment that the GC and the JVM has behind it, so you might run into problems. Okay, so that was introduction and some background. Let's talk terminology. And why do we need terminology? Because the words matter, and we need to agree on what they are. Who here knows what a concurrent garbage collector is? Okay, a good number of you. How about a parallel garbage collector? Fewer than concurrent. So this is a common situation I run into because the words are very similar, so we need to define them. A concurrent collector is a collector that does its work without stopping your application while the application is running, concurrent with the application. A parallel garbage collector is simply a collector that can use more than one thread to do its job. These two things have nothing to do with each other. They're not interchangeable. You could be concurrent and not parallel, parallel and not concurrent. You could be both or neither. This is what the words mean. And the reason for this confusion is partly because the words in English mean very similar things, and when they get translated, they mean very similar things. And partly because if you go 30 years back in academic papers, you'll find papers talking about parallel collection as what we today call concurrent collection. So there's confusing written material on the subject too. But this is what everybody in the GC world means in the last 10 years at least when they talk about collectors. So let's define some more terms. Stop the world. You've heard this a lot, I'm sure. You've experienced it a lot, probably. A stop the world collector is the opposite of a concurrent collector. Something has to be totally stopped for the collector to work while the application can't move. Incremental, usually associated with stop the world. An incremental collector is a collector that can do its job in parts, stop the world parts most of the time, but not monolithic parts. So for example, you can have a monolithic piece of work like what a copying collector might do, move everything from here to there, and you can't stop them in the middle, so that's one big monolithic stop the world, or you could find a way to increment through it. Do a little bit of work, get to a place where it's safe to let the application run, then do a little more work, and so on. So incremental usually means slicing up the stop the world into smaller pieces. And there's some interesting incremental collectors out there now. The last word, which is really important to explain, is the word mostly. Mostly means exactly what you would think it means, but you need to look at how it's being used in describing collectors and algorithms. Mostly means not always. Mostly means sometimes this won't happen and it won't hold. And that's what it means. Otherwise it wouldn't say mostly. So mostly concurrent means sometimes it will stop the world. Mostly incremental means sometimes it will be monolithic. Okay, it's a nice escape way of saying the opposite of what you're saying. Some more definitions. Precise versus conservative collectors. And you all live in a world of precise collectors if you're programming in Java. A conservative collector is a collector that's not quite sure where all the pointers are. There may be pointers in places it doesn't know about. There may be things on the stack that it doesn't know if they're a pointer or an integer that looks like a pointer that happens to have a value. And when a conservative collector collects garbage, it needs to treat things that are actually not objects as objects, because they might be. And it also has a serious limitation because it can't move objects around. If an object needs to be moved and you need to change all the pointers to that object, if you see an integer that happens to have the same value as that pointer, it's not a good idea to change it to a different number. That would be a bad thing. Or if you don't know where some pointers are and you didn't change them, you end up with a dangling pointer to a bad location. Precise collectors are the opposite of this. It's a collector that knows exactly where every single reference is in the world and whether or not it is a reference at the time that it needs to do garbage collection work. You have to be a precise collector to move objects. You need precise information at least about the objects that you're moving. And every precise collector gets support not just from the collector knowing this, but most of the work involved in this is actually the compilers. The JIT compilers need to produce information about every code point you might be stopped at and where every reference is on every register and every stack location at that code point. That's a lot of information. Information normal compilers simply don't produce. So when you leave here, thank the JIT compiler writers, because they've produced a lot of information that lets precise GC happen. All the commercial JVMs you can get your hands on today are precise collection JVMs. Okay, so it's a category that's common to all of them. And predictably, every single one of them has a moving collector. It will move objects from place A to place B at least once in the lifetime of the JVM. So I talked about this preciseness. Well, the preciseness is not there all the time. It's there, if I have a running thread that's moving around and a collector that's running concurrently with it, that's a moving target. It doesn't have information about everything all the time. So the places at which we have information are something we call Safepoints. A garbage collector's Safepoint is a point or a range of execution in a thread where we know where all the references are. Where an external thread can actually look at this thing and find every reference and follow it or manipulate it or change it safely. That's a GC safe point. There are other types of safe points, not just GC. And I often will switch and talk about both the same way. But an example of a non-GC safe point is a de-optimization safe point. That's a safe point where you need more than the information about the references. You may need to know things like where all the variables are so you can change representations of your stack and things like that. When we say bring a thread to a safe point, we mean get it to that point and don't let it execute past that point. Now that sounds like nitpicking, because that sounds a lot like let's stop it there, right? But very importantly, there are running threads, a lot of them often, that would be at a safe point but consuming a lot of CPU. And a JNI call is a great example of that. Every time you call native code through JNI, you're crossing into a safe point. The entry to the JNI, we know where all the references are. JNI could run for an hour. It could invert a big matrix. But it doesn't modify any references or change their locations until it gets back onto the Java side. So it's at a safe point. And what the collectors do is just stop it from getting back, not stop it from running. So being at a safe point does not mean being idle. It just means not progressing past the point. You need safe points to be frequent. If they're not frequent, and one thread might take 10 seconds to get to a safe point. If we're trying to get to what we call a global safe point, everybody will be waiting and that guy still didn't come. And you get a big pause and no work done in that pause as a result. When we talk about a global safe point, that's the system bringing every thread to a safe point. That's usually your stop the world pause, and collectors will do that in various points or phases in their work. So we covered some terms. Let's look at what's common to all these collectors. There are three things that all precise collectors do. First one is find all the live stuff. The second one is deal with the dead stuff. And the third one is move objects around. Every collector in every JVM does all three of these things. None of them avoid them. Examples: mark, sweep, compact, commonly used in all generation collectors. Map one-to-one to these. Mark is find the live stuff, sweep is deal with the dead stuff and put in a free list. Compact is move it together so there's room as you have run long-running programs. But copying collectors, often used in young generations, are another example of these three things. A copying collector will move all the objects from a from space to a to space. Just pick all of them, everything you can reach, and move them over, and when it's done, the from space is empty. That's an example of doing all three things in one pass. It finds all the live stuff, it deals with the dead stuff by freeing the entire from space, and it moves every object. So all precise collectors do these. Let's get into a little bit of detail and some intuition into what the work means, what the workload looks like for a collector. The mark phase, when collectors that have marks, is pretty simple. We start from something we call the roots, static variables, threads, and we scan all the reference we find in them and paint them, kind of follow through every reference and mark that's alive, that's alive, that's alive. And then when we look at an object, we reach it, we look at all the reference in it, and we mark all those. And we basically follow and paint everything we can reach through all the references that we get to from the roots. At the end of a mark pass, everything that's alive will be marked alive, and if it's not marked alive, it was not reachable from the roots, so we can collect it. It's that simple. This is why circular linked lists are not a problem for collectors. If you can't reach it, it doesn't matter how it's constructed. And if you can reach it, it's not garbage. The work involved in doing this is linear to the live set, to how much data is alive, not to the size of the heap. You can grow the heap as much as you want, with the same number of objects, the same number of references, same amount of work. It's not going to change. Sweep is even simpler than mark. You scan the entire heap from start to end. You look at those mark alive or not things, and you take all the dead stuff and manage it somehow, usually in free lists. So you basically have lists of these empty holes in the heap. And that's all sweep does. Find the dead stuff and put it in recyclable areas. This work is generally linear to the size of the heap, not to the live set. It doesn't matter how much you have alive, it matters how big the heap is, because you're going to sweep every part of it. Okay? Compact. Well, why does compact exist? Over time, if you run long enough with variable size objects, you'll get Swiss cheese holes in your heap. And what will happen is you get objects of different size allocated and collected and allocated and collected. And those free lists that you have empty spaces in them that they're tracking, but you may not have an empty space big enough for an object that comes in. You can have a heap that's 90% empty, but I'm trying to allocate a 10 kilobyte object, array of some sort, and there's just no 10 kilobyte hole in this thing. It's gotten a lot of small holes in it. Compaction deals with the fragmentation of memory by moving objects together and creating longer contiguous regions. It's an absolute necessity to compact in any long-running application unless you have a fixed set of object sizes that never changes in number. Anybody here process XML? You don't control your object sizes, okay? You have variable size objects. You will get Swiss cheesed over time. There's nothing you can do about it. So compaction is necessary. In compaction, we have two main things. One is we relocate objects. We move them to a new location. That's the easy part. The second part is what we call the remap, which is finding every single reference in the heap that might point to this object and fixing it to point to the new location. You move one object, there may be 3 billion things that point to it. You need to cover every one of them. So the remap is the hard part. The reason the remap exists is why we usually compact a lot of things at the same time, because we're going to scan all the references that might hit it anyway. We may as well scan it on behalf of a lot of moved objects. Compaction work is linear to the live set. As complex, as scary as it is, it's only linear to the live set. You only visit all the live references and all the live objects. You don't have to deal with the empty stuff, and if the heap grows, the compaction work doesn't grow with it. Okay? So that was the mark, sweep, compact phases. Let's look at copying collectors. Copying collectors are simpler. They start with a from space, and they move everything to a to space. I covered that before. At the beginning, everything's in the from space. Everything points to the from space. We start with the roots. We take every object we find, we move it to the to space, and everything we find inside of it, we grab all the objects that they point to and move them to the to space. At the end, everything's in the to space and everything points to to space. We're done. Single pass. Complexity, it's linear to live set. Okay? So we covered some basic mechanisms here. Let's look at their qualities. A copying collector has an interesting downside. When it's standing on its own, you need twice the heap size to be reliable. Because when you're starting a copying collector, you have no idea how much dead stuff there is or there isn't. So you need as much room, and you've just filled up this thing. You don't know if it's empty at all. So you need as much room in the to space as you have in the from space. Otherwise, you could get stuck and not be able to complete. It's an interesting limitation. A mark compact collector typically has a similar limitation, but it's not quite as bad because it needs that much memory in order to reliably compact the entire heap in one pass. But if it doesn't have all that space, it could just stop somewhere in the middle. Copying collectors tend to be monolithic. It's all or nothing. Mark, sweep, compact, which is, not just mark and move, but sweep and compact in place, can compact in the same space, so they need only as much memory as 1x plus a little bit to make to work, which makes them more efficient in memory. And both copy and mark compact are linear only to the live set. Mark, sweep, compact is also linear to the heap size. Right, so larger heaps make those slower or bigger. You may be able to avoid some compaction. There are variants that do mark, sweep, and sometimes compact. We'll cover some of those. And I already talked about the copying being monolithic. You just check on time and see how we're doing here. Good. So, last little mechanism before we go into some more interesting stuff, generational collection. Who here knows what generational collection is? Good amount of you. So generational collection is based on a simple observation called the weak generational hypothesis. It's the observation that most things we allocate die pretty quickly. They die young. That's not the same as saying that most objects are young or die young. Most live objects are actually old. But most of what we allocate dies almost immediately. And we use this observation to create efficiency in garbage collectors. So if we could somehow focus our collection effort only on things that were recently allocated, and this statement is true, that most of that is just dead stuff, then we could apply a collector that is linear to the live set and get a lot of heap size back for it. So for example, if my young generation is only 1% alive, and I use a copying collector, it's linear only to that 1%, not the other 100, then it'll be very efficient. We only have to copy the live stuff, we get, copy a little bit of live stuff, we get a lot of dead stuff back. And we never even look at it. When I said before, we don't spend any cycles looking at dead matter, the copying collector doesn't look back at the from space at all. It just moves the live stuff away and boom, we've got gigabytes of empty memory. So that's a very effective way of gaining efficiency. And we can only do that if we deal with the exceptions to it. So some things will survive there and will stay alive, and we have to move them out of that area or that assumption will stop being true. So we have to focus our collection only on the stuff that is sparse, only on the stuff that will tend to be dead and young. And if something isn't that, like some stuff I read up and put in a cache and it's lasting for a while, we have to move it elsewhere, promote it into what we call the old generation of it. And that has to happen or the entire thing won't work. So there's efficiency that comes out of this. It's usually an order of magnitude plus, 10x, 20x, better efficiency on garbage collection from this simple trick. It's been around for about 30 years. So every JVM uses that. It's almost a necessity if you're going to run on commercial servers these days. When you look at how this thing works, how do we do this trick of collecting only the young generation? We use something called a remembered set. Remembered set is basically a way of tracking all the references into the young generations that are not in the young generation. Things that point in there from other parts of the heap. And usually it's a due generation system, so basically the remembered set tracks all the places in the old generation that are roots for the young generation. We treat them as roots, we start marking or copying from them, and then we get to focus only on the young stuff and not look at the old stuff until we collect that part. The remembered set is critical. Without this, you couldn't do generational collection. The other cool thing about generational collection is that 2x annoying behavior of a copying collector is no longer needed. If we use a copying collector for the young generation, but a mark sweep compact for the old generation, we could just overflow to the old generation if we have that rare case where there's not enough room in the 2 for the from. Anyone here tune survivor ratios? That's what you're playing with, right? You're hoping that the 2 is big enough, and if it's not, it just goes to, it's just prematurely promoted to the old generation. It doesn't crash. It's a good news. I mean, otherwise you would need a survivor space as big as the Eden to survive. Usually, I said I won't tell you how to tune collectors here, but a trade-off that's very important in young generation and generational collection is to keep the object lifetime and survival behavior right. You want to have things survive in the young generation more than once, more than allocated and immediately go old if they happen to be alive when we hit the young generation. And that's because at the point where we collected the young gen, there's a whole bunch of stuff that was just now allocated. It's going to die in a few milliseconds. It's just unlucky enough that we collected now. So you tend to want to let them live at least a cycle so that they'll age out and they'll die there and you won't promote too much. But on the other hand, if you let them live too long, hundreds or thousands of times in there, then the whole assumption that that thing is sparse will go away. It'll have old objects, 25, 30% of it will be alive, the efficiency will go out the window. So you need to get it in that range. Luckily, that's not a hard thing. it's pretty easy to get the young generation size right for these things. It's not super sensitive. So how does this remember set thing work? I told you what it's for. How do we track it? So we basically need to track every reference that we store outside of the young generation that might point into the young generation. And a common way to do that is something called card marking. It's not the only way, but it's practically the way most commercial collectors work. And card marking works by saying for every heap address or range of heap addresses, we have something that says there's a root in there, or maybe a root in there. So every time I store a reference there, I'll also mark a place there that says in that word or in that 512 byte range, there's something, you need to scan that as a root, see if it points into the young generation. We use a write barrier. A write barrier that means every time we store a reference into the heap, we also do this card mark. And the JIT compilers emit that write barrier on every Java store. It's actually 2 stores, right? Now, there are variations of this. Hotspot typically uses what's called a blind write barrier. It's a pure store of a 1 there if I stored there. But there are variations of precise and conditional ones that say only store a 1 if it's a pointer from the old to the new, or only store a 1 if it's not already a 1. And there's actually a flag for tuning that in Hotspot. So that's how that thing works, typically. So putting these together, let's look at what the combos look like. Most commercial systems, most commercial JVMs are generational. Most of them will have a young generation that is a copying collector. And most of the time, it's going to be a monolithic stop-the-world copying collector. By now, you should understand every word on this slide. Okay, I defined them, I believe. The old generation is usually a variant of mark sweep compact or mark compact, and it could be any of these combos. It could be it could be stop-the-world or concurrent, or mostly concurrent, or incremental stop-the-world, or mostly incremental stop-the-world. Okay. I'm not going to define all these terms. I'll tell you that the mutator is you guys. You guys sit there and mutate the heap, so the collector actually has to deal with that. Monolithic stop-the-world is an important definition. We covered a bunch of the others here. But later, if you look at these slides, these are all important terms to understand in garbage collection. Here's some important metrics to understand in garbage collection. Again, I won't define all of them, but some ones to highlight. Allocation rate. How fast you allocate objects. Pretty intuitive. That allocation rate is typically linear to your work rate. Not knowing what your application does, I can guess that if it's allocating 100 megabytes a second when you're doing 100 transactions per second, it'll probably do 200 megabytes a second when you're doing 200 transactions per second. So how fast you go and how fast you allocate are strongly tied to each other. Mutation rate. That's a little less intuitive. That's not how fast you make objects, that's how fast you touch pointers. How fast you're modifying where things point and storing on top of them, so we have to deal with them. And that too is almost perfectly linear to your work. Double the work, double the mutation rate. If your collector is sensitive to these metrics, that's an important thing to understand. Because a collector might work perfectly well or within certain SLA parameters as long as allocation rate is not beyond X, or as long as mutation rate is not beyond X. And it'll work perfectly well until it just stops working perfectly well if you go 1% above that point. So finding that breaking point and the point of sensitivity is important. Marking time and compaction time are also important terms because they tend to dominate. Something's wrong with the clicker. They tend to dominate pause time if pause time exists. So let's talk about some trade-offs. And this is here's how the machine works, and you can deduce from that what flags to set. Trading CPU and throughput and memory. So I'll give you a couple intuitive limits to understand how memory and CPU on GC works. Both of them are easy to understand. The first one is that if I had a gigabyte of live stuff and 1 byte of dead stuff, it doesn't matter what collector I use and what algorithm I used. Every time I allocate a byte, I need to find that byte in a gigabyte. It's a lot of work. So it's going to spend a lot of CPU doing that, and GC will be all you do. And you're looking at a gigabyte to get 1 byte. You're not going to be doing much work. That's an intuitive point. It's extreme thrashing. The other intuitive point is that if I had infinite memory, I would never have to garbage collect it, so I won't be spending any CPU on that, right? And between the two, there's an almost perfect 1 over x line. Graphically, it looks something like this. Here's your live set. You have to have at least that to work. And there's an almost perfect 1 over x line that reduces the amount of CPU you spend on garbage collection as the empty memory grows. If for the same live set, increasing the heap size increases the efficiency of garbage collection to an arbitrarily small number. Remember I told you this is the most efficient way you could do allocation? Allocation in a contiguous region for garbage collection, which most collectors do, and simply a bump of a register pointer forward. That's all it does. There's no smaller amount of work you could possibly do. Well, it actually checks to see if it's past the point, and it bumps it, so it's 3 instructions. But that's faster than any malloc or any free list or any other mechanism could possibly do. Now, what do we pay for that? Every once in a while, we have to go collect the memory, and that's going to be work, but we can control how much that work is. Empty memory buys you efficiency with garbage collectors, and empty memory is a cheap resource, especially these days. So that's how efficiency in collectors work. Now looking at it a little more, what we're saying is empty memory and CPU power are basically interchangeable here. Not for your application, for the collector. Unfortunately, I can't give you that for your application. And the way to understand that is this. Both copy and mark compact collectors are perfectly linear to the live set, right? They recover all the empty memory in that, but the amount of work they do is kind of fixed by the live set. And if I increase the empty memory, I reduce the frequency of how often I have to do a fixed amount of work. That's why the efficiency is there. So copy and mark compact have this perfect doubling of efficiency every time you double the empty heap. What do we control with this? As I said, it's all about efficiency. So we control how much work we do. We also get to control how frequently pauses happen if they do happen. So doubling the empty heap will half the frequency of pauses. But we don't control the size of the pauses with this. Okay? The size of a pause is not getting any better when we increase the empty heap. It's just how many cycles we do per allocated byte that gets better. In fact, in a mark sweep compact, the pauses will grow because part of the work is linear to the sweep, to the heap size, and we'll get larger pauses. It'll still get more efficient, not in a perfect 1 over x, slightly less than that, but it'll still be more efficient with heap. This is the reason most people don't apply this tool, because above a certain size, the pause size is going to kill you. You're going to be very, very efficient, but you can't handle the pause. It looks a lot like a crash. So that's why you don't go all the way with that often. But it is a very handy tool. Doubling the young gen size is a very effective way of reducing GC percentage. So we talked about pauses a little. Let's talk about some techniques to deal with them. So far we've talked about very simple mechanisms. But what if we're doing all this stuff while the application is actually running? So let's look at concurrent marking. Concurrent marking is, I'm trying to figure out what's alive while you're changing what's alive. And there's a classic race, we call the concurrent marking race, that goes something like this. The collector is marking, painting what's alive. While this is going on, your application is taking a reference the collector hasn't seen yet, copying it and putting in an object the collector has already visited, and erasing that reference, changing it to something else, putting a null in it. Now, if it did this and the collector kept marking and didn't notice that this happened, at the end of the mark phase, this object would not have been marked live. The collector would think it's dead and really bad things would happen. So every concurrent marker has to cover this case. It has to make it impossible for you to move that around and for it not to notice. There are a few techniques for doing this. The most common one in current commercial collectors is a multi-pass marking technique. And it goes something like this. The collector's doing the marking, you're doing the mutation, and while you're mutating, for everything you change, there's a tracking information going on, something that tells us that got changed. So the collector finishes its mark, it goes back to the beginning and says, let's visit all those things that got changed. And could do that concurrently while you're running, but that means you're making more changes. And eventually you're hoping this list gets small to the point where you're willing to do a very small stop the world pause and just catch up with it. Okay? That's a mostly concurrent multi-pass marker. This works. It works pretty well, except that it's sensitive to mutation rate, highly sensitive to mutation rate. Double your throughput, there's twice the number of these things, right? At some point you may be mutating faster than the collector can rescan, and you'll fall behind. Or maybe it can scan that fast, but it's taking long enough that you've run out of empty memory, so what's the point of being concurrent? If any of you are using the CMS collector, you've seen this happen if you've ever seen the message concurrent mode failure happen. Or this is one of the reasons for it. But this is an effective technique at not doing perfectly stop the world marking. Another interesting technique is not concurrent, but incremental compaction. So we look at the compaction, it's a big thing. Every time we move an object, we have to scan the whole heap. That's a big mess. Can we do it with a smaller pause or smaller part pauses? And the way incremental compaction works is that we look at regions and we carry these remembered sets where every region knows what other regions pointed to it, not just old to new. And the collector looks for sets where here's a region that only has 23 other regions pointing to it. So if I move objects in this around and compact it, I don't have to scan the whole heap, I just have to scan 23 regions. And here's another region that has another 20, and these 20 and these 23 actually overlap. So I could do work for both together. And the collector looks for these sets of regions where it can do the compaction and the remapping work in a contained pause, in some target number. And if it can find it, it'll do it and then do a good job. It does have a few downsides. One of them is n-square complexity. When you grow the heap, the number of regions grows. And the number of regions pointing into any one regions grow. Statistically, that's where your n-square comes from. You can combat that by making bigger regions. That hurts the pause time granularity, or you can combat it by allowing for bigger pause times. But if you want constant pause, you're going to have an n-square complexity problem. There are other issues with popular objects. If a region has one object in it that half the heap points to, it doesn't matter what the other objects have in there. And you could get stuck with the whole heap having a popular object in every region. And the heap could be 99.9% empty, but you still can't compact it without a full pause. But this is a good filter. In fact, filters are what we've been doing for about 15 years. I call this delaying the inevitable. This is the classic way of building better and better collectors over time. What we do is we try to avoid the hard thing by pushing it into the future and putting a filter ahead of it. Generational collection is a very effective way of avoiding old gen pauses. Then within the old gen, we can try not to compact them and recycle them in place, but eventually fragmentation will force us to compact. And if we compact, we could try and do that incrementally, but eventually we're going to have to deal with the popular objects. All these are moving problems to be more rare into the future. Very effective ways of getting efficiency and reduced occurrence of pauses, but not reducing pause size. So let's classify the collectors. We're here at the classification point, and I just need to check on my time. Sort of okay. Typical collectors, I've already said this. This is how they're going to fall into categories. So let's start with the simplest, most common collector used in Java. A hotspot parallel GC collector. The reason it's the most common one used is because if you're running on a server and you say nothing, this is what you get. It's the default collector. It is a monolithic stop the world copying NewGen. Simple. And it's a monolithic stop the world mark sweep compact old gen. I'll stop and let that sink for a second. The next one, which has been around now for a little while, it's used in production on a lot of servers, is the Concurrent Mark Sweep GC, also known as CMS. So this is a mostly concurrent collector that's very popular these days. So remember I said what mostly means, right? Here's the classification of the young generation for this mostly concurrent collector. It's a monolithic stop the world copying NewGen, very much like parallel. The word concurrent only applies to old gen in this collector. In the old gen, we have a mostly concurrent, non-compacting old gen that uses a mostly concurrent marker. It's that multipass marking scheme I talked about. Works pretty well up to a throughput point. It has a concurrent sweeper, but since it doesn't compact, it has to fall back to something, which is a full stop-the-world GC on about 12 different possible reasons. That's the biggest part of the mostly. Sometimes it's not, and will fall back to a full GC. Another popular collector, well, experimental recently turned into production collector, but we talk about it a lot, is the garbage first collector, G1 GC. And by the way, this classification actually holds exactly the same for the J9 balanced collector, from my understanding of it at least. But here I could actually read the code, so I know what it does precisely. It is a monolithic stop-the-world copying new-gen. It has a mostly concurrent all-gen marker, similar but not quite the same as CMS. It has a stop-the-world mostly incremental compacting all-gen. This is a quote from the design criteria for this collector. It's to avoid as much as possible doing a full GC. That means it does a full GC. That's its fallback, okay? So that's how you classify these. Now with that, I'm gonna switch quickly to the problem that I was talking about before, and that's that stop-the-world garbage collection is becoming a serious issue. And remember that I asked you guys this question and got some polling results, right? Well, what's the problem with this? How many of you program to servers? Yeah, a lot of you. Well, this is a server. That's a $5,000 server from Dell, or a $10,000 server from Dell. And most of you, the vast majority of you, fall in a category of using somewhere between 2 to 4% of a modern day cheap commodity server. That is a problem. It's a problem in many ways, not just your problem, it's an industry problem. And you know, today's servers are just powerful, abundant in memory, abundant in CPU, and our individual application instances seem to be tiny parts of that. And we often have rationalization of why that is, but it's just an observation that that's what's going on. Our application instances, for whatever reason, are having a hard time making good use of cheap hardware. And that problem is growing fast at Moore's Law rates. It's not a slow problem. Now, I often raise this point and people ask me the obvious question of, come on, 4 gig is a lot of memory. Who needs more than that? And my answer is, you know, this question's been asked and answered many times over history. Some people made a lot of money after answering it wrong. But generally, intuitively, this does not last, okay? So is there a right number? We're right now arguing whether we're, you know, 6 gig or, you know, it just moves. And by the way, Bill Gates says he never said that, so that's the actual quote from him. But the actual target here moves. There's a point in time where it's right now this number and then that number, and it moves at about 50 to 100x a decade, which is pretty fast. Looking at it over history, I like to track something I call the tiny app history. Tiny apps are those things that you build, and if you broke them into pieces, you'd be embarrassed to tell your family about them, or your friends. I track tiny app history over time, over my memory, and it used to be 100K, then it was 10 meg, then it was 1 gig around the .com era. And these are the servers we put them in. And usually if an app can be handled by a computer that's cheap and easy to get, it's kind of silly to break it into 100 pieces. If I took a 1 kilobyte array and wanted to sort it, and I said that I did that by spreading it onto a dupe farm with 1,000 nodes in it and got it and reduced it back, that would be interesting, but not something to be proud of. Now, if it was a petabyte right now, that would be necessary. So it just moves over time. Well, here we are in 2012. A 1/4 terabyte server costs less than $10,000. Less than any server on there. What should the tiny app size be that people are not embarrassed to talk about? It should be around 100 gig, but a lot of you were not embarrassed at all to talk about, you know, 4 gig, 6 gig, 5 gig. And that's okay, because you're doing the only thing that works. The memory wall looks like this. About a decade ago, the ability of Java to handle large heaps stopped happening. And people stopped growing the heaps with them. And the thing that's actually causing this is garbage collection. It's pauses in garbage collection. So at some point, we don't like to build apps that pause for 3 minutes at a time, so we don't do that. We stop at the point where people are unhappy but still live with it, which is a few seconds. And most JVMs will stop for several seconds at a time at the heap sizes that you've stopped at, which is why it happens. And the root cause for this is this link between scale and responsiveness that's causing that. And just checking on time. Yep. So GC is responsible for it, but a lot of things in GC are not responsible for it. It's not about efficiency. It's not about the size of the little things. It's not about the frequency of them. It's about the fact that bad things happen and customers or bosses will see them. So we just don't like to build broken systems, and that's what's keeping us at small memory sizes. It's tiny percentiles of overall system size. So we can look at the non-monolithic stop-the-world problems that are causing this and how to deal with them. So here's the most common way we deal with them. It's very effective. And it's surprising how often that happens. So let me explain how this works. You run a test, you say 40 minutes is enough, and there's no pause in it. Now, if you ran it a little longer, you would have seen a couple glitches, and you say that's a measurement error, right? And then, you look at a day and it looks like this, and people are calling you at night, right? So one way is to just say, yeah, I know it happens to everybody, I'll deal with it later. This is another cool way to deal with it. Creative language. We rename terms to make the problem sound good. This is an actual quote from an actual JVM's guarantee. We will guarantee a worst case of 5 milliseconds 99% of the time. This is actual marketing material. 1% of an hour is 36 seconds. I can pause for 36 seconds, but guarantee 5 millisecond worst case response time, 99% of the time. That's an honest statement. Okay, just rename the problem. Mostly, that's a common way of dealing with the problem. There are other things like when you set goals for projects saying that, you want it to be fairly consistent. Not consistent, fairly consistent. It's okay if sometimes it's not consistent. Or, typical pauses will be in a few milliseconds or tens of milliseconds. That means some pauses will be a lot bigger than tens of milliseconds. That's what they're saying there, but it sounds nice, right? Now, there's actual other ways to do it, and that's to measure stuff. I've actually put a public domain tool called JHiccup up on our website, and it produces charts like this for any JVM and any application. It basically documents the incontinuity of execution of your JVM. The fact that the JVM, when doing nothing, was not doing anything. So if your app was actually trying to do something, it would have seen worse response times than these. And you can run this as a Java agent along with your app to see what's happening. You could go to our website to see what that's like. But how do we get past these? What can we do technically to solve them? And I've got only about 3 more minutes, so I'll run really fast. We need to solve this link between stop the world stuff and scale. And we need to eliminate stop the world fallbacks. Well, here are the 3 things that seem to be hard to do. Concurrent compaction, concurrent marking that is robust, that runs at any rate that you allocate and mutate, needs to happen for you not to fall back. You need concurrent compaction, at least in parts. And you need to be able to do young generation stuff that doesn't stop the world, because the only reason those don't bother you right now is your heaps are tiny. If you had a 100 gig heap, your young gen would have a 2 gigabyte live set to promote. That would look like today's biggest pause. All 3 of these have to be solved, or we won't solve them, and or we won't get past this stuff. And that's just saying the same thing. So let's classify yet another collector. Remember, I told you I'm going to do that. And now I apologize that I'm going to tell you how great our stuff is. But using classification, right? We have a concurrent, guaranteed single pass marker. Doesn't matter how fast you mutate, how fast you allocate. This will finish marking concurrently in one pass without stopping the world. Key quality. Has a concurrent compactor. It can move objects around, and it can remap references without having to stop your application at all, okay? It has a concurrent compacting all generation. That's the combination of those 2, but it also has a concurrent compacting young generation. It is not a stop the world young gen. So even at hundreds of gigabytes of heap and young gens that are only 2% of that, it will still work very concurrently. Most importantly, it has zero stop the world fallback code. The code simply doesn't exist to stop the world as a fallback. That's the primary quality. Now, this is not the only way to solve this problem. There's probably 7 other academic algorithms out there that could possibly do this. This is the only commercial one that exists right now. So that's what Zing does. And I'm not going to get into these because there's a full paper about them, and we don't have the time. But let's look at the benefits. So this is an academic paper thing, so it's got a reverse logarithmic graph in it. But the upper right is the good part. And what you're seeing there is the worst case response time getting smaller as you go up against heap size. And this is for a given workload. Allocates about a gigabyte a second, it's at about 2.5 gigabytes of live set. What you're seeing here is that C4 as a collector reaches a plateau very, very quickly and stays there at the couple 10, 20 millisecond worst case. Other collectors get worse as heap size grows. And you should by now understand why that is, because the worst case grows with it. This green line is actually C4 with generational collection disabled. That shows you why generational collection is effective. We get to do the same work, we get to reach the same stability on a lot less memory because we're a lot more efficient. For Zing, the only reason we have a generational collector is this, because our pauses are no different. But we get to be more efficient in CPU and speed and everything else. Another way to look at the benefits is what it does to application behavior and tuning. So I told you I won't teach you how to do this. Right? And I won't teach you why that flag is exactly the opposite of that flag because it's a different application. But I will teach you how to tune Zing. This is how you tune Zing. Now that just replaced about 3 one-hour talks I've heard in the last couple of days on how to tune G1 and how to tune CMS. You don't have a lot of tuning to do because there's one big currency you use, empty memory. There's no downside to using it. There's all the upside in efficiency and higher location rate that's sustainable because of the math I showed you before. So you could just use that as a big stick, and it's cheap. Another way to look at it is, what does it do for application behavior? Well, sustainable throughput is different than unsustainable throughput. Okay, this is a really fast car, but not a sustainable way of driving it. So, the way I look at that is how many users can I run in a box without breaking my SLAs, not how many users can I run in a box. And this is an example of running, some number of users in a box and Zing running 17 times as many users in a box because we cheat. We get to use 50 gigabytes of memory instead of 3 gigabytes of memory because we don't pause and the machine has them. So another form. And the last way to look at it is, I told you about J-Hiccup. This is Charles Nutter explaining to the world why we built it. And honestly, that's probably the reason why we built it. But it looks something like this. Zing is on the left, CMS is on the right. Can you see pictorially how much better we are? Probably not. Let me highlight the numbers. That's a 14-second pause, that's a 20 millisecond hiccup. Or normalized, it looks like this. That's the result of using a concurrent collector on a real application. So that's pretty much the summary of the content for the collector. The one additional thing to look at is when you're looking at low latency applications, trading applications, places where all gen has been tuned to happen once a day and we restart at night, you can actually take these collectors down to the handful of millisecond worst case and make them work pretty well. So if you're interested in that. And last, before we go, we put up an open source project initiative where people can use Zing for development and test in open source projects for free. So if people are interested, our booth is now closed, but you can come to our website. So that's it. Sorry for running a minute over. I think we might have some room for Q&A if people are interested, and we'll see when they kick us out.
I tried to post this presentation.
This will be posted online. They already took the slides, so it should be there. I'm not absolutely sure.
On the internet.
Exactly. Yeah. I give them the slides. They'll go along with the talk somewhere.